Good morning, good afternoon, good evening, and bon appetit to everyone. Welcome to today's session on water pollution for the Copernicus Marine Service. I'm Florian Caillon, Training and Capacity Development Officer at Mercator Ocean International, and I'll be guiding you through this session. Today, we're diving into the Copernicus Marine Service platform, what it is, the powerful data and products it offers, and how you can use them. By the end of this session, you'll not only understand the key features of the platform, but also see practical examples of how these tools can be applied to monitor and address water pollution. So let's get started. Before we begin, let's quickly go over some house rules to make sure you enjoy this session to the fullest. Please don't use the chat box on your right-hand side for questions. It's there for greetings and for sharing links with participants throughout the session. If you have a technical or content-related question, we invite you to use the dedicated Q&A section. You'll find the Q&A button at the top of your screen. Simply click it to open the dedicated space where you can ask your questions to our speakers. We'll have a Q&A session at the end of each presentation. And while you're there, you'll also see a quick survey about today's webinar. Feel free to fill it out anytime during the session. And I will leave the floor to Daria.
Thank you, Florian. And hello, everyone. My name is Daria. I'm going to be your second moderator today. And well, I'm going to just quickly tell you about the participant guide. So we strongly recommend you to go to the website of this page, official event page, and check the guidelines and also the resources. So the guidelines will just tell you all the kind of rules, for this event. And for resources, sorry, for resources, you will find all the materials used for this event there. And for the next part, we're going to go through the agenda. So first, Florian, who you already know, is going to present you a short introduction to Copernicus Marine Service. Then we'll have a more in detail demonstration of MyViewer by Anaïs Piren, who is from Mercator Ocean as well. And then we'll have the first user testimony by Knut-Frode Dagestad, who is a researcher from Norwegian Meteorological Institute. Then we'll have a short virtual coffee break where you can a bit rest from all the information you just received. And we will move to the second part of our event with a second user testimony by Oliver Samlas, who is a junior researcher at Tallinn University of Technology. And then it's going to be the third user testimony by Alexandra Rosa, who is a researcher at Madeira University. That's it for the short agenda. And the first speaker is Florian, who is going to give you an introduction.
Thank you, Daria. And before we wrap up the agenda, I'd like to share an important note, is that we'll have a second session on Thursday, where we'll dive deeper into practical tutorials. This will cover Python, QGIS, and R, all focused on the topic of water pollution. And this will be a great opportunity to get hands-on experience and learn how to apply Copernicus Marine data in real-world workflows. So make sure to join us for that session as well with the same link. And now we'll start, so as Daria said, with the small introduction of the Copernicus Marine Service. Copernicus is the European Union's Earth observation program. Launched in 2012, it has grown into one of the world's leading sources of operational environmental data. Its mission is to monitor our planet and provide insights into how Earth systems are changing over time. To achieve this, Copernicus provides free and open data along with information covering the atmosphere, oceans, land, climate change, emergency management, and security. Each of these services follows the same principle: provide reliable, long-term Earth observation data that anyone can access at no cost. Today, we will focus on the Copernicus Marine Service, implemented and operated by Mercator Ocean International. This service delivers high-quality and regularly updated ocean data, describing the ocean's physical state, sea ice, and marine ecosystems, supporting science, policy, and industry worldwide. The Marine Service portfolio combines three complementary sources. First, satellite observations, provide global coverage and continuous monitoring. Second, in situ measurements taken from buoys, floats, and research vessels. They offer a local precision. And finally, these observations serve as the foundation for validating and optimizing the ocean models that the service provides. The Copernicus Marine Service offers a vast catalog of ocean products. You can access real-time conditions, historical reanalysis going back 30 years, and forecasts up to 10 days ahead. Its coverage extends across the global ocean and key regional seas around Europe, making this resource invaluable for both research and operational applications. The Copernicus Marine Service data supports a wide range of sectors, from science and innovation to coastal monitoring and policy development. We group these applications into 12 blue markets, aligned with the 3 pillars of the UN Sustainable Development Goals, which are environment, society, and economy. These examples show how marine data translates into actionable knowledge for decision-making. To describe the ocean fully, we organize variables into 3 families. The blue ocean represents physical processes such as temperature, salinity, currents, waves, winds, and sea level. The white ocean covers sea ice variables like ice concentration, thickness, velocity, and age. And the green ocean contains biogeochemical and ecosystem indicators, for example, chlorophyll, nutrients, oxygen, carbon variables, or pH. Together, these 3 families provide a comprehensive view of ocean state and health. So how do you access all this information? Everything is available through a single portal, which is marine.copernicus.eu. After free registration, you can browse and download from the data store harmonized datasets, mostly in NetCDF format, making them easy to use across scientific and operational tools. From the homepage, click Ocean Products to open the catalog. The catalog is your main entry point. Each product is a structured collection of datasets with descriptive metadata. Filters on the left help you narrow down by areas, variables, or time range, making it easy to find what you need. Clicking on a product opens its dedicated information page. Here you will find details like spatial and temporal coverage, as well as resolution. You can download the data through the Data Access tab using several available protocols. Supporting documentation, like the product user manual, is also linked there, along with direct access to online visualization. And beyond downloading data, you can explore it visually using our online tools accessible via the Ocean Visualization tab. Copernicus Marine Service offers 3 visualization tools, each tailored to different needs. The first one is My Ocean Learn. It is perfect for education and outreach. You can explore ocean variables on a globe with rich ocean literacy content, videos, and simplified views. My Ocean Lite is ideal for quick interactive exploration of the essential ocean variables like temperature, current, ice, pH. You can access live data, zoom into regions, view forecasts, and share. And finally, My Ocean Pro is designed for advanced analysis. You can dive into detailed datasets and choose the ones that fit your purpose, depending on how they are produced. So satellite versus in situ versus model outputs. You can perform custom queries, export data, and access high-resolution graphs for research and professional use. We will now make a demonstration of how to use some of the main features of the My Ocean Pro viewer. And for that, I will leave the floor to Anaïs Perrin from the user support at Mercator Ocean.
Many thanks, Florian, and hello everyone. My name is Anaïs from the Copernicus Marine User Support team. So I will share my screen like this. All right. So in this presentation, I will introduce you the different feature of our data visualization tool, the My Ocean Viewer Pro. So to access the My Ocean Viewer from the homepage, simply click on sorry, I move the windows. Click on the Ocean Visualization here. And you will find our 3 different ocean visualization, the MyOcean Learn, Light, and Pro. And we will interesting in the MyOcean Pro, which is the most advanced and the one we will use here. So when you first open the MyOcean Pro, you will see default layers already displayed on the map, such as the seawater velocity, the potential temperature, the concentration of chlorophyll A. You also have small blue eyes next to the layer's name, shows that the layer is visible. You can hide it or display another one like this, and even change the priority order by dragging them up or down, for example. By hovering your mouse over the variable's name, you will see details information about the product, the dataset, and the variable itself. Any layer you don't need can be removed by clicking on the cross here. On the interface, you can also change the projection by clicking on the arrows, here for the North Pole and here for the South Pole. You can also click and drag the map and zoom in and out using your mouse wheel. For today's example related to the water pollution, I will focus at the mouth of the Ganj-Brahmaputra rivers here, which discharge a huge amount of fresh water, sediments, and nutrients into the northern Bay of Bengal, especially during the monsoon season. So in MyViewer Pro, we will look at 2 key variables for this region: the salinity, which traces the freshwater input from the river, and the variable KD 490, which we use here as an indicator of water turbidity. This is what let's see the low salinity river plume and the highly turbid water spread from the coast to the open ocean, illustrating how river discharge and water quality are closely connected. So to find a product, we need to click on Add Layer here, and this takes me directly to the Copernicus Marine Data Store. So these products are classified in different ways. The most popular, the recently open in the interface, the favorite, the new in Copernicus Marine, and so on. Under each product thumbnail, you will see the product long name and the product short name, the data acquisition mode, its model, or here in situ, or even satellite. You also have the area and the spatial resolution. You also have the temporal resolution. For a 3-dimensional product, you will see the number of depth level next to the spatial resolution. And you also have the information about the variables it contains. On the left, you will see the filter panel. So by default, you have the simplified filter interface with a few key criteria such as variable, area, and time range. This is very convenient to quickly narrow down the catalog and often enough to find the right products. You can also switch to the advanced mode here, which exposes the more detailed filters such as the universe, the main variables, all variables, area, and so on. And this view is more precise and useful when you need a very specific product configuration. So in my first example, on the KD variable, I will use the advanced filters because I'm looking for a very specific product with a very specific characteristic. So then I apply the following filters. In all variable here, I will select the light attenuation. And for the area, I will select the global ocean. In the source, I will introducing the satellite observation. And for the processing level, I will select the level 4 for interpolated data. In general, in the catalog, the dark thumbnail corresponds to the near real-time product, while the lighter thumbnail is multi-year product, which have a longer time coverage based on the reprocessed time series. And for her study in the Ganj plume, and it's a long-term seasonal signal, I will focus on the multi-year product. So clicking on the product redirects you to the product description page, where you will see an overview of the product, as well as example here of product use cases, and the classification section, which details the product parameters. On the left-hand side, you have several tabs. The notification here, where you can track incidents, improvement, or maintenance, current or past. You also have the data access tab, which lists all the data sets in the product and the different downloads method. For each data sets, you have the time period for which data is available and links to the available services, subset files, and maps. And the small information buttons here will take you directly to the related Help Center articles explaining this download modes. You have the contact tab to reach the user support and the documentation section with useful links to documents such as the user manual, quality information documents, scientist's quality overview, a link to the roadmap, the license, and an article on how to cite the product in your work. So the user manual contains technical data, while the quality information and the scientist's quality gives scientific backgrounds and information on acquisition modes. You also have the DOI links, which redirects you to the catalog the product page. And at the top, the share icons allows you to copy the URL and share the product page. So to visualize a variable, click on Add to Map and then select the variable of interest. So the filter I used previously links directly to the relevant dataset, but I can access all other dataset of the product by clicking on All Layer here. So I will select the daily dataset of KD 890 here, and I will click on Add to Map. So the fixed button here indicates that the dataset does not have data for the day specified in my visualization here tomorrow. By clicking on the button directly, the viewer directly displays the latest available data from the dataset. So next, I want to add the salinity from the global physical model product. Again, I will click on Add Layer, and I will clear the filter. But this time I will stay on the simplified filter interface. In the variable, I will select the salinity, and in the area, I will select the global ocean. So these two criteria alone made it easy to highlight 12 products. I will therefore choose the multi-year product model, so the second one here, and then I will click on Add to Map, and I will select the daily salinity dataset. And I will click on Fix. In addition to Copernicus Marine Product, the MyViewer Pro can now also open and display NetCDF data coming from other providers, as well as your own NetCDF file. So at the top of the viewer, you can see the small upload icon here. When I click on it, I can here drag and drop the NetCDF file, or click on it, click to select it from my computer up to 2 GB, and optionally activate the store in my own bucket and name my datasets. So datasets are kept for a limited period of 7 days, but they are not automatically deleted when they are stored in the user's own buckets. On Add Layer here, you can see 3 tabs on the top. Sorry, I just moved the bar. The Copernicus Marine Service, it's the catalog, the personal catalog, and other providers. So the other providers tabs, I will clear the filters again. The other providers tabs links data from external producers that are compatible with the Copernicus, with the MyViewer Pro. The personal catalog tabs list the dataset that I myself upload earlier using the upload icon. So this is a dataset containing the seawater velocity for the Northern Bay of Bengal from May to December 2025. So I click on it, and I will click on Add to Map and add the seawater velocity to my visualization. All right. Oh, sorry. All right. So now I will close it and remove this layer. So now we have all our layers and we can see icon on each of them. The download icon to download the data, the information icon, which takes you directly to the description page. So here is my file, but here is a description of the salinity dataset. Okay. The layer icon, which to switch to another variable in the same product. The gear icon to customize the layer, and the log icon to apply a logarithmic scale. So I will focus on the gear icon here. So for the customization, you can change the opacity of the layer. You can also change the style, solid or hatching. So hatching lets you highlight area according to a value. And for example, here for the key D variable, I will show only key D variables values greater than equal to 0.1 meters, for example. All right, so to highlight the most turbid waters influenced by the river plume, I can also change the color map or invert the color map. You can also use the discrete color steps where you can add, remove, or redefine the thresholds. You can also set the minimum and the maximum values for the gradient. And for example, for the salinity, I just want to see salinity between 0 and 25. And you can choose whether to hide values outside the range by clicking on this icon here, Mask Out Layers. You can also click on the auto to automatically adjust the minimum and the maximum values to the map view. For vectors layers like the seawater velocity, you can change the style to solid, solid plus particles, solid plus vectors, or hatching. You can combine them, but here for more visibility, I will keep in the particle style. So the particle styles makes the surface circulation much easier to see and clearly show how the current can transport the low salinity, high turbid waters from the gauge plume offshore. At the bottom of the screen, the bar shows the variable period of data. The whitest line indicates the period of time for which the data is available for all the open layers in the visualization. You can zoom in with your mouse wheel, or you can also use the right and left arrows on your keyboards to navigate through time here day by day, because I have opened the daily datasets. On the right here, under the objects and settings, you will see the depth scale. So this scale is visible because I opened the salinity layer set at depth. So by default, the data shown the surface data, but I can click directly on it or use the up and down arrow on my keyboard to navigate step by step in 10 meters increments. And I will reset. Okay. So just above, you can create some points. You can also create lines. Oh, sorry, lines. Or even an area. like this. So each object show its coordinates here, and the transect length for lines and area size for area. You also have the values for points or an average values for area and lines of the opens variables. You also have the minimum and the maximum values. Each graph, each object generate graph, time series, or depth profiles if the data is 3-dimensional. The graph menu here, in the graph menu, you can click on adjust axis, allows you to manually enter the start and end date. You can also download the data in NetCDF, CSV, or SVG format, and delete the graph. And you can also add a new graph based on the variables at the bottom of the window here. So I will make some space for better visibility. So I'm going to merging my two objects here. Oh no, by my line. So I just want to make my point here, and I will merging my point and my area object here. So this is very useful for comparison purposes. So here my object E is my area, and my point F is my point located offshore. So now from the graph, I will also maximize the windows. So from the graph, we can see that near the river mouth, surface salinity here follow a strong seasonal cycle. So outside the monsoon, it rises above 25, and then during the monsoon, it drops sharply down around 5. For key D values here, I will just remove this graph. For key D values at the river mouth, remain above 0.1 meter throughout the air, indicating presently weakens turbid waters, and as soon as we move away from the coast here, this pronounced seasonal cycle salinity weakens, and the KD only rarely exceed the 0.1, which is consistent with clearer and more oceanic waters. So you can also import geometries in your visualization by clicking on Import here. And you have the Preset tabs where you will find various collection of geometries. The Recent tabs allows you to find geometries that you have previously opened on your interface. And then the WKT, GeoJSON, and Shapefiles tabs allows you to define or import geometries into your viewer. And for example, I will click on the marine ecoregion here, and I will search for the northern Bay of Bengal, and I will import it into my visualization. Okay, so now under the import function, you will find the settings, from which you can log out, log in, change the base map color, show toponings, here change the projections, or define the units, and much more. So now, to download the data, I will click on the download icon of the variables I'm interested in here. For example, the volume attenuation coefficient. So you need to be logging. If not, the viewer will prompt you to do so. And as a reminder, the registration is free. In geographic area here, you can either type manually your coordinate or use the define on map option, which allows you to directly create your desired area on the map, like this. Or you can also click on Define on Map and select an existing object. So reminder that the download will cover the bounding rectangle of the object and not only the exact shape. You also have the date range, which must be within the time period variable, and you can use the As in Map button to match to the currently displayed dates. For three-dimension layers like the salinity, you have another section, the depth range. It lets you enter the range of interest, and you can also use the As in Map option. And you have the also download section that allows you to download several variables contained in the dataset at the same time. So when you're ready for the download, for example, here and like this. So when we are ready for download, you can click on the download button for direct download from the interface up to 800 megabytes. Or you can click on the automate button, which generates a download template for Copernicus Marine Toolbox. So this method allows you to exceed the 800 megabytes limit imposed by the online downloads. So two templates are proposed, one executable from command line and another from the Python interface. And you can also click on Browse Files buttons for retrieving the original files as distributed by the producers, usually organized by years and then months, and covering the full area. If you need assistance, you can click on chat bubbles at the top, talk to an expert, so the widget will open and you will be able to chat with Blue, our AI agent, in the message tab here, or you can also request to chat with a human agent. You can also access the Help Center article directly on from the Help tab here without leaving your page. And if you type, for example, MyOcean, you will find an introductory article here. And I would like to draw your attention to the Q&A section at the end of this article, which you may find very interesting. Here is the Q&A section. So next to the bubble here, you will find the share icon that allows you to share the links to your visualization. You can also create an image or a video, and you can also generate an embed link to add to your own platform. And finally, you have the information icon here that shows statistics on the volumes of the data downloaded each week in MyOcean, and also list the available keyboard shortcuts for a smoother exploration. So to conclude, I would like to remind that many articles are available in Help Center about the MyOcean viewer and more. And the user support team is always here to help you if you encounter any difficulties. So thank you all for your attention.
Thank you, Anaïs, for your presentation. I will start sharing my screen again. Before we move on to the next speaker, we want to make this session as interactive as possible. So if you have any question, we'd like to hear from you. It's really easy. Just click on the Q&A tab on the event page, or scan this QR code with your phone and type in your question. We'll be collecting your questions throughout the session and addressing them during the Q&As. So don't hesitate. Your input help make this discussion even richer. And also, after this, our second session on Thursday, you will receive the replay of both sessions, the presentation slides, and your certificate of attendance. So now let's dive into the questions for Anaïs. So for our first question, Someone asked, how do I select a product when the area is located in more than one region? For instance, Catalonian coast is included in global, Mediterranean, and Atlantic.
Yeah, you have the global region. The global product cover all the ocean, not lake, but cover all the ocean. So you can find the data for different region, like Mediterranean and Atlantic. So it is explaining. So yeah, I think that I answered the question.
Yes. Our second question is there any download limits for a normal user?
For online download, you're limited to 800 megabytes. But if you use the Copernicus Marine Toolbox, there are no limitation. Your own limitation is your bandwidth.
Okay, thank you. Someone is wondering how all the data is collected. Is there areas in the world that are less covered?
It's depend of the product. We have several producers, and each product are prepared and is different. You need to consult the documentation of the product to learn about the data acquisition mode. That's
Okay. Can we put specific coordinate as a point?
Yeah, sure. You can use, for the moment, you can use the WKT geometries. So in the import settings, here, import geometries, you have the WKT function, and you can create points and enter its coordinates and click on the import button, and then you will see the exact object in your visualization.
Thank you for your answer. The next question is, can we download data in Excel format?
Yeah, you can download data in CSV format, but it's readable in Excel.
Nice. The next question, wave height, salinity, these data are available for how many years past?
This depends on the product again. We have a multi-year product and near real-time product, and it's depend of the producers and the type of product. But if you have a question of if you have if you need some help in the search for a product, you can ask Blue, for example, or even ask for a human agent, and we are glad to help you.
We have another question on the resolution. So what is the spatial resolution in the Ocean Viewer and how we can validate the data?
Spatial resolution of the Ocean Viewer. I'm not sure that I understand this question. What is the spatial resolution in the Ocean Viewer?
I would understand like if kind of like some pixels, if you have like very detailed to the meter in some areas, or is it like a kilometer square?
The resolution you have in the settings, you can change the projection used in the viewer. Equatorial is EPSG 43 and 26, or the North Polar projection or the South Polar projection. So we have 3 different projection in the MyOcean viewer, but I'm not sure that answer your question. But I can answer after
Yes.
after this presentation.
If some questions were not fully answered, as Anna said, you can go directly to the help center or the user support. You can send them a message. I don't know how many questions left we have. For the next one is, can we expand the graphs with the time duration and find out the detailed data per month?
So in the graph, you can set the start date and the end date. You can zoom directly on the graph. And if you find on details data per month, for example, you need to see monthly data sets. So you can search in the catalog and select the temporal resolution like a monthly, and then you will see all the data set proposed, and see the graph and download the data in the graph. And that's it.
Okay. Someone asked if we can combine different layers to download in a single file.
No, for the moment you cannot download several products in the same request. You need to download your data separately, a request for a product. But you can download several variables if it's variably contained in the same dataset.
Thank you for your answer. Are there any data related to marine pollution or plastic pollution in the catalog?
Not directly, but we have some use cases. In your page, but we not have a specific variable for marine pollution, I think. But you can enter to the use cases and watch some other project about this thematic and see what product they're used.
Okay. Can data downloads be automated in order for providing daily updates on services using the data?
Yeah, you can automate your download using the toolbox, for example, with in command line interface or Python, and you can automate your request. Yeah,
Okay, nice.
it's possible.
We will have a more detailed presentation on the toolbox on Thursday, right?
Yeah.
Yes. We had other many questions, but in order to keep the time, we will answer them in a post event report that you will all receive after the event.
Thank you.
And we'll be able to continue the webinar of today with the presentation of Knut-Frode Dagestad from the Norwegian Meteorological Institute that will talk about using CMS data for operational drift modeling in the ocean. Knut-Frode, the floor is yours.
Thank you. So good morning. So I'm working at the Norwegian Met Office. So we are one of the data providers for Copernicus. But in this presentation, I will act as a user because I will show how we use CMS data for operational drift modeling in the ocean. So this illustration shows several of the applications of drift in the ocean. So in the center, we see the toolbox we're using, which is the Python open source tool OpenDrift, which has modules for different drift applications. So you can see, for example, at the bottom, an oil spill scenario. And to the right, you also have search and rescue, typical drifting persons or objects or small boats. Also largest ships without engine power can be drifting. And you want to model how they drift to help the rescue operations. And plastic pollution is also a well-known topic, for example, or microplastics like objects, but also microplastics, smaller particles. But there are also applications like fish eggs or marine larvae, or icebergs, or atomic pollution, or pollution from ships. So these are several of the applications that exist, and we have some operational service for the most critical of these, typically the oil spill and search and rescue, which is a 24/7 service operated by our forecasters on duty. And we have a 30-minute response time requirement. so that within 30 minutes of receiving information about an incident somewhere, we shall deliver the drift forecast and some weather report to accompany the rescue operation. So the main users are listed here. So these are the Norwegian governmental users. For example, the joint rescuing centers, the oil companies, and the coastal administration. So this service is not open for the general public because for two reasons. One is that it actually involves computation, so it has some computational cost. And also, although it's not very difficult to make a simulation, it requires a little bit of training so that you make meaningful simulations and not at least meaningful interpretations of the results. Yeah, so this schematic is showing how the service works. So starting at the right, you see again the OpenDrift tool, which is open source Python that anyone can download and use. So it doesn't itself contain any forcing data, which is typically currents and winds or waves. But at the lower right, you can see that you need to ingest forcing data that can be either local files that you have or remote data. And this is where Copernicus come in. That's one of the main data sources that we use for our forecast. So if you know Python, you can use it through the Python API, or you can use the built-in graphical application that comes with OpenDrift that you see at the top right. But seen in the center of this slide, you see we have made a web service around this setup called Drifty, which is an open API machine interface. And that's a web service, so that on top of this, you can make different types of user interfaces. For example, at the upper left, you see it's called Vario. That's the web interface that we have made for our own users, or actually also used by our internal meteorologist to help their service. But some of the users, for example, the coastal administration or the oil companies, have their own web interfaces or their own GIS tools. So they have several of them have integrated this drift service into their application, so that they can initiate or start a simulation, whether it's oil or search and rescue, from their own tool. And the simulations is running on our service using, for example, Copernicus data, and the results are then visualized in the GIS tool of the end users. And some users have actually also made a mobile app that is using the same interface. So that means you can run the simulations from the app, although the actual simulations is then run in the cloud and on our service, but it's visualized and initiated from the mobile app. So for the forcing data, we have a list of forcing data because we want the service to be robust, always up and running. So this is showing a typical configuration where we have, for the first priority on the Norwegian coastline would be our own very high resolution coastal models. But as soon as we are outside of them, we jump over to the Copernicus products, and you can see some CMEMS or Copernicus products in the lister, both the winds, waves, and currents. And in addition to this, we also have external, like the HICOM global ocean model and the NOAA or American wind forecast as a backup. So I now will show some examples of real cases of recent incidents. So this is showing one incident from 2020. And you see the picture is a lot of plastic pellets that was observed in the beaches of Oslo in the upper right of the map in April that year. So there were all over the fjord, it was covered by these plastic pellets. And for some time, it was not known what was the source of this pollution. But there were many candidates, and one of the candidates is the red dot that you can see on the map. But that was 1.5 months earlier. So one ship had lost a cargo container of these pellets. But these pellets are used all over the world, so there are many. So it's not obvious link between that incident and these observed on the beach. So, but the simulation can help answer that question. So we were asked to do the simulation, and you can see to the left animation of simulated drift using then Copernicus currents and winds. And you can see to the right the observed plastic pellets, and there's a very nice match both in space and time with the pollution. So this was actually used as a proof in the trial, and this company had to pay the rescue operation. And another recent case, not pollution, but this is an example of a search and rescue. It was a lot in the Norwegian media. There was a woman that went missing last year from Kristiansand in the south of Norway. And 40 days later, the body was found in the ocean close to Shetland. And it's not typically a place where the currents will drift, so it was not obvious that she was drifting for there. So it was not certain what had happened. So again, we can use the simulation to help solve this criminal case. So again, we made a simulation, and you can see the animation to the right. And this animation is for 40 days, and we see that it is actually realistic that the body drifted from where she went missing to where she was found. And yeah, so in this case, it was actually not the current, because the current wouldn't normally go that direction. But you see the wind product that we see in the background here. So there was actually quite strong easterly wind in exactly this period. So that made it feasible that this was the natural case of this incident. And here you can see the script. So this is actually just the 5-line of Python code. So that's actually all you need to do this whole simulation, including making this animation with the wind background. So you see here in the line number 2, we are adding the data sources. So first, our own high resolution model that covers just the very coast. But as soon as we're outside of the coast, that is for most of the simulation, we rely on the Copernicus global ocean model and also the global wind product. Yeah, so we were also asked to get some user experience with CMEMS data, how we use them. So just first, I would say our requirements for the operational service is, of course, we need a very high uptime and availability. So our service, we would actually demand our 100% uptime. And this we achieve by using several backup data providers as shown. So although Copernicus is maybe the most important and reliable, we have also other backup sources so that if it should be unavailable for some reason, we have almost guaranteed that we have a backup data source. And it's also very important to have a fast access and download. And that also means subsetting and streaming, because you never know where an incident will happen. And we don't want to download data for the whole world. That would be a lot of unnecessary data download. So we don't download data before we need them, and only for the area that we need. So it's only when you start the actual simulations that we do download the needed wind and currents. And fortunately, this is very fast, though. It only takes a couple of minutes to make a typical 2-day simulation. And also for operational services, it's very important with standards, both the standard format and the access method. So CMEMS is using the CF, or Climate and Forecast Convention, that has become a standard, fortunately. So this means it's basically plug and play. When there's a new product coming in, it will immediately fit into the simulation, and we don't need to make any adjustment based on the products. So this is also very important. Yeah, so just a brief history. So we are today using the Copernicus Marine Toolbox, but before that we used the Threads or OpenDepth service. And before that, again, we used the Motu client, which was another toolbox. So back in the days, we had a lot of OpenDepth data sources that you see to the right, for example, our own data and American data and different data sources. But in those times, we needed to use a special Motu client for the Copernicus Marine service. And as far as I remember, I think we also needed to pre-download to a local disk before we could use them. So although the client was not bad in itself, this was a bit unfortunate because we needed to maintain two different solutions. And in any operational scheme, you want to make it as simple as possible, because that any complexity or moving parts add to the complexity and decrease the robustness. But then later, also Copernicus complied with the opened up data service, and that was much better, because then we had the same solution for all the data providers. Although we needed also the password for the Copernicus, but there are solutions for that as well. So actually, with the new Copernicus Marine Toolbox, we're actually a little bit back to the same, because we need a special solution for Copernicus. But at least now we don't need to download to disk before. We can stream directly from the data source, and that's a huge benefit. Yeah, so the Copernicus Marine Toolbox, it's actually very well made. It's fast and reliant, and it provides CF standard data products. And it also returns X-ray data sets. That means we can work with the data just as if it was a local file. And this is also very, very convenient and makes the much easier to develop and also maintain the operational scripts. So actually, I think we have just maybe one wish, because there are wind products, but only up to present. But for situations where there is a request for simulation from now on to the future, which is of course very relevant, it would be nice to have also the winds from the Copernicus. And especially it would be nice if all the current ocean current products could contain the winds that were used for the forcing, because then we also have the consistent wind and current data set, and that's also a big advantage. So I think I heard some rumors that wind forecast will come to Copernicus, and I think that would be very much welcome. And just a few slides to the end about easy access, which I think is, to my opinion, vital, because if you have a best product and another product, you would naturally choose the best product. But in the case, if the other product is good enough and the best product is, we need to register and there's a password and there's a specific solution, but the good enough product is more easily available, many users, including also myself, would then actually use the good enough products. Yeah, and recently we are also starting using Wikio and Edito online platform, and in the OpenDrift documentation we added some extra documentation or help to install OpenDrift on these platforms, including how to add the username and password, and that works very well to use it in the Jupyter notebooks, so that you don't really need your own Python environment anymore. You can just do everything in the browser, and it's very convenient to set up and use. Yes, so that was my last slide. Thank you.
Thank you, Knut, for your presentation. It was really interesting. And we have a few questions coming in. So I will start sharing them. The first one being, does OpenDrift have backtracking functionality?
Yes, it does. It wasn't shown here, but you can simulate any simulation backwards, both oil and search and rescue.
Okay. And can it be used on inland lakes to track elements affected by wind?
Yes, there are also examples of that, for example, in the Caspian Sea, and so yes, that's possible. And in fact, also in the air, in principle. There's not the most applications for module in OpenDrift are in the ocean, but there's nothing wrong with making things in the drifting in the atmosphere.
Okay, nice. Is the plastic pellet use case open source? And when can someone learn more about OpenDrift and how to effectively use it to model surface plastic accumulation on coasts?
Yes, so this plastic pellet use case is actually very simple, because in this case we just assume that the spheres or pellets was floating at the surface, and it's quite well known by both theory and experiment that anything floating in the ocean would drift with typically rule of thumb is the current plus 3% of the wind, and more wind if there is object, for example, small plastic boats that sticks out of the ocean. So it's very simple to do this simulation, and on the OpenDrift webpage, there's a lot of tutorials and examples that can be adapted to specific needs.
Okay. There's a more general question on what is the difference between forecasts and prediction in your presentation.
Yeah, I'm not sure about the semantics here, but to me, it sounds like the same thing.
Yeah.
I think it's the same to me, yeah.
What if the region is too small? Is there a scale issue?
I'm not sure what it means that the region is too small, but I don't think there's any lower bounds to the area that you can simulate. The only thing is, if you, for example, if you want to make a simulation inside a very fjord or in a very small coastal environment, then maybe you need a higher resolution coastline than the one that's provided with OpenDrift. But you can easily add your own, for example, shape finds for the coastline.
Okay. Apparently, you said you need training to have projects in drifting. Do you provide training?
Not really, because that's not our service, but there's a lot of examples and a little bit of tutorials and documentation on the OpenDrift web pages, and there's also other resources around. And yeah, I don't have the link for it, but I can mention there's a new online community developed or initiated by the university in Utrecht. It's called CLAM. It's a community for drift in the ocean where anyone. So if you just Google CLAM, CLAM, and community, you can enter the community and you can ask any question. And there's a very, open, friendly environment to learn and share experiences.
Nice. You mentioned this is used by all companies. Is it also used in aquaculture context?
Yes, for example, in Norway, there's a lot of salmon industry, and there's a problem with the salmon lice, and they use chemicals, for example, as one of the means against the lice. So there are other, not ourselves, but other users that are making modules, for example, for the salmon lice, how they drift, including the swimming and these kind of things. But also the chemicals that are added to the salmon farms are also maybe sometimes sinking and will affect the seafloor in the environment locally. So that is also an applications that people are using, because OpenDrift is made a way that you can make your own modules for your own applications.
Okay. Is there a model available for sewage, for example, from shore stations, treatment plants, for concentrations over time in an area?
There's no ready-made model for sewage, no. So that would need to be made by someone that has, I don't know what that would involve. Maybe some, I don't know, chemical transformations or drift. So yeah, no, it doesn't exist, but it could be made by someone who knows a little bit of Python.
Okay. For our next question, sorry. When using environmental data such as winds and waves for tracking plastic drifts, which environmental data plays a larger role in drifting, for the winds or waves?
Yeah, that's a good question, because it's not obvious what is because that depends on the case. For floating plastic, winds, as I said, is typically 3% of the wind. And that can, in many cases, that can be more important on the currents, depending on the weather situation in the area and the local currents. So generally, I would say it's equally important. And there is also waves, but what's very often done is that you don't need the waves really, because you can just include a wave effect in the wind drift factor.
Okay.
To a good approximation.
We reach also the end of our Q&A, but we will take a few more, and the rest I will invite you to send them after the webinar, so that everyone can also have an answer to their question. The next question is there any plan on making the platform deployable on premise?
I'm not sure what that means, that someone can set up their own web service. There's no specific plans for that, but it could happen in the future. So by now, people would need to use the Python tool, and can of course make their own platform around that if needed. But we have no immediate plans to make it the platform deployable, because there's a little bit in-house specific setup.
Okay. What data source prediction models do you use for forecasts?
Yeah, that can be anything actually. It can, typically any Copernicus project that contains winds and waves can be used, because they are CF compliant, so they would plug in immediately. But we also use, as I mentioned, our own high resolution wind and waves and current models for our own fjords. And there are many data sets around the world, typically on OpenDAP, but there are also more clients coming, like, for example, NASA are providing currents also with their own clients, similar to the Copernicus Marine Toolbox.
Okay. And finally, is it possible to work with the data without downloading, for example, as COGS?
Yeah, I'm not sure what COG is, but well, you need to download the data, of course, to get it, but you don't need to download that files and store it on your disk. You can, for example, like with Copernicus, you stream it directly from the toolbox, same as with OpenDAP, so that you just get a small minimum area covering the incident, and will be downloaded in memory and used in memory, so you don't need to maintain any files, which is very convenient.
Okay. Well, thank you very much for your presentation and for attending and participating in this webinar today and presenting how you can use the CMS for your own projects. Thank you very much, Knut-Frode. And we will now have a short break of 10 minutes. For a short coffee break, we will be back at 11:15 for the next presentation of Oliver Samlas, 11:15 CET. And yes, see you then. And during the coffee break, if you want to answer this short question that I will share, don't hesitate. Welcome back, everyone, to today's session, Ocean Sessions, water pollution. We will keep going with the webinar, and I will leave the floor to Daya for the moderation of the second part. Daya, the floor is yours.
Thank you, Florian. So yes, I am back for this part, and we will start with the second user testimony with Oliver Samlas presenting you Baltic Sea replication assessment using SMEMS. So Oliver, you can turn on your camera and your mic.
Yeah, so hi, I'm Oliver Samlas. I'm a PhD student / junior researcher at Tallinn University of Technology, and my presentation will be on the Baltic Sea eutrophication assessment using Copernicus products. Yeah. Now a little background info. I've been working with Copernicus products for about little over 5 years. It started with the EuroSea project, and our work package's aims under EuroSea were to demonstrate how Copernicus Marine Service products can be used for eutrophication status assessment, and also to demonstrate whether the quality can be improved by simulating more vertical profile data, which was then done by the DMI, or Danish Meteorological Institute. And finally, to communicate the results to main stakeholders, which in the Baltic Sea case would be HELCOM. And all of the results are also available as reports. Now, how it's done, or as I said before, in the Baltic Sea region, HELCOM, or Helsinki Commission, targets this problem and has a goal to mitigate the human-induced eutrophication. Now, to do that, HELCOM has coordinated action to reduce the nutrient load and in turn improve the Baltic Sea environmental status since 1974. It also carries out joint monitoring and assessment in the Baltic Sea area since 1979, and the first periodic assessment was published in 1986. And the latest assessment, what they call the HELCOM Holistic Assessment, is HOLAS 3 for the period of 2016 to 2021. Now, how did it do it? Is with these core indicators that have been developed by experts and then adapted by HELCOM and contracting parties, which are the countries around the Baltic Sea, and they reflect the achievement or non-achievement of good environmental status, or GES. Now, this indicator-based assessment system evaluates the environmental status based on 3 classes, which are the nutrient levels. You have your nitrogen and phosphate there. then the direct effects, which is chlorophyll A and cyanobacterial bloom index. And finally, you have indirect effects, which is the water clarity, oxygen depth, shallow water oxygen, and bottom fauna. And to ensure the high confidence of these assessments and to minimize the potential influence of natural variability, long-term and systematic measurements are required. Now, how do they do it? Is with these, they make these indicator reports, and on the left side, you can see an example of it, of the chlorophyll A indicator. And for each indicator, they calculate the AQR, which is the ecological quality ratio, which are then scaled after normalization to 5 classes of 0.2 width. And then you get the eutrophication quality ratio scaled. And what that shows is the present concentration in relation to the reference value, which decreases along with increasing eutrophication. And on the right side, when all of these reports are done for individual indicators, they make this integrated eutrophication status where you can see the overall condition of each basin. And as you can see, this is done for each assessment unit. And for this work, we were concentrated on the open sea areas. And along with these, also you have the confidence level on how confident they are in these results. And as I mentioned before, you need long-term and systematic measurements to for it to have high confidence. Currently, however, routine marine environmental monitoring, including the actual acquisition of some of the parameters needed for the indicators, is being carried out with too low spatial and/or temporal resolution. On the left, you can see an example of the Estonian open sea monitoring stations, which there are 19 that we visit 6 times a year. And on the right, you can see this is NO3 parameter that I took from the ICS database, the same database the HELCOM uses to make the assessments. And here you can see the positioning of the stations. And this is for the period of 1993 to 2021. And as you can see, there are big areas where there is no data. So obviously Copernicus data could come in handy here. And we did an example with the dissolved inorganic nitrogen, which calculations are based on HELCOM methodology as average concentrations in the surface layer, which is 0 to 10 meters for the period of December to February. And as you can see, this is absolutely doable with Copernicus data. But now, when we actually look at the concentration values or the indicator values at the end, we also were able to do a comparison with 2 different products, because 2 years ago, I think the production team changed in the Copernicus behind the reanalysis, and we used both of them. And why we used the reanalysis is because reanalysis already incorporates the in situ actual measurements into it. And as you can see, these are 2 of the central basins. The red line is the new model, blue line is the old model, and black is the HELCOM results. And in central basins and southern basins, the results did get better. And if we look at the more further away you move from the central basins to the east and north, you can see there's discrepancies in the data. And absolutely, especially with Gulf of Riga, because it's a shallow basin, and also it's cut off from the main water with shallow sills, so it's also harder for the model to work with. So as you can see, the red model or the new model actually got closer, but if you look at the scale, the old model was so off that even though the new one got closer, there's still like 3, 4, 5 units difference. Now, we also carried out the status assessment based on the dip concentrations in winter. And on the left, you can see the HELCOM monitoring results, and on the right, the reanalysis results. And the evaluations results differ a lot between the analyzed parameters, indicators, and subbasins of the Baltic Sea. In general, the model dip concentrations and indicator results agree better with observations than, for example, tin or chlorophyll A. However, the largest biases of dip could be both negative, which is the case in the eastern Gulf of Finland. It overestimates the values, or sorry, underestimates, and positive, which is the case in the Botnian Bay, where it overestimates the values. And as I mentioned before, the further away you move from the central basins, the harder it becomes for the model. And now we also did the integrated eutrophication status assessment, which is all of the available indicators, which we use thin dip, chlorophyll A, and oxygen depth. And on the upper panels, you can see the monitoring, HELCOM monitoring data. And on the lower ones, you can see the Copernicus reanalysis data. And on the left side, you can see the upper and lower is the simple mean, where we just averaged the indicator results. But on the right, we did the HELCOM criteria group, which is that each indicator has its own weight. And when doing that, we found that it primarily poor eutrophication status was found in all of the basins, but overall model-based assessments gave a better eutrophication status in almost all basins compared to the HELCOM results. And the comparison of the two applied aggregation methods showed that if the HELCOM aggregation method was applied, the eutrophication status assessment actually improved in multiple basins. As you can see, compared to the simple mean with the model products, the central basins, the Eastern Gotland Basin got better, as well as the Botnian Bay on the top, and also the central and parts. Now, this is from the quality document of the reanalysis model. And as you can see, the model validation is done with quite, or the stations used in the validation are quite sparsely situated in the Baltic Sea, especially with basically you can go more east from here and from more north from here. So all of the three basins that I mentioned before are also the ones that are the most different compared to the validation results. Now, we adopted a quality evaluation which is better suited to a specific indicator, considering only relevant seasons while using data from all monitoring stations in each assessment unit, not only a few offshore stations like here. And we compared the modeled indicators as well as modeled parameters, individual parameters with monitoring data indicators and monitoring data parameters. And the evaluation results differ a lot between the analyzed parameters. In general, model dip concentration and indicator results agree better with observations than dip and chlorophyll A. And for the entire Baltic Sea, the present quality evaluation gave worse results in, for example, the root mean square deviation for indicators such as, or parameters such as NO3, NH4, and PO4 than the method used in Copernicus. And that we think can be explained by excluding seasonal variation from the evaluation, which are qualitatively well simulated by the model. That means high nutrient concentrations in winter and low concentrations in summer. Also, what we found, we also compared the model output bias based on full year and seasonal data sets. So again, as you can see here, the Copernicus validation is done for the period of 1993 to 2018. But we use the seasonal data. So when the thin and dip indicator use December to February, we only took that data. And what we found was that NO3 and NH4 had large negative biases in both evaluations, and the seasonal evaluations gave worse results in most of the subbasins. Now, there could be many sources for disagreements between the model and observations. like mainly availability of observational data, including monitoring station network and temporal location or temporal resolution. Also model resolution, data assimilation, different kinds of forcing, model topography and configuration of the basins, as well as oversimplification of biochemical processes, for example. We conclude that most discrepancies between the model and monitoring results originate from the numerical models used. But still, nevertheless, the indicator and basin-wise analysis demonstrates the use of models in evaluating the adequacy of the monitoring scheme in the Baltic Sea. And the method can be easily transferred to other sea areas and indicators. Now, in conclusion, the quality and applicability of Copernicus marine service products vary depending on the indicators, subbasins, and models. The present reanalysis product underestimates this dissolved inorganic nitrogen, chlorophyll A, and oxygen depth. And the eutrophication status is most challenging to simulate in basins with high freshwater input, ice cover, and complex topography. That is also the case for the same three basins to the east and to the north, especially again the Gulf of Brigham. And we think that more observational data and biochemical data assimilation are needed for model output improvements, which is also an interesting thing in the old and the new reanalysis comparisons. The old model incorporated also nutrient data, while the new one didn't, but there were still. There are also a lot of work done by other people who found that only incorporating temperature and salinity data, depending on the model, could improve the nutrient levels or make them even worse. So there's more work to be done there. But still, overall, Copernicus is available. I think more people should use it. And currently, they are not used in full. So closer cooperation with potential users is needed to build up the trust. Thank you.
Thank you, Oliver. That was a nice presentation. Very interesting. We have some questions for you. So the first question is, what is the success rate of your predictions in a general case?
This sort of statistical analysis of this we haven't done, but still the central basins, essentially the basins where there are more data available to incorporate, as well as where the data is more like situated over the basin, you get overall better results. But the Baltic Sea is still quite hard for the models because we have Baltic Sea is shallow, but still there are the thermocline and holocline that are situated at different depths. So that makes it really hard. Also, the occasional ice coverage, the topography of the basins, all that affects. So it's really basically what you need and where do you need it. That really affects the results.
Okay, thank you. For the next question, is it feasible for an for a narrow river that changes its course frequently?
I don't really know if it's applicable like that, because there are huge basins that we use them for, or what could it be for a narrow river? Because basically what we're looking at is where the basins where the nutrients and all those like collect. The river, I don't know how you could be. I think it wouldn't be applicable like that.
Okay. Yeah, okay, maybe the question was just not very nicely stated. Next question is, can we see the project code in GitHub?
We really haven't done that because that was essentially the methodology used is HELCOM methodology. Each indicator has its own indicator report, which has the methodology. It's essentially like I mentioned before with the thin example, that it's the top 10 meters for December to February. But yeah, we haven't done that.
Okay. Okay. The next is how Copernicus is useful for eutrophication studies in rivers of mangrove areas. I don't know if it's very applicable to you.
Yeah, because as I mentioned before, it really depends on the overall location, because as the Baltic Sea is a brackish sea, also, the Danish sills, it's like a very specific area compared to, for example, the Mediterranean Sea, also very different. So I think the mangroves are, again, as I mentioned before, most people or more people need to use it. You need to check and just carry out the tests.
Okay, thank you. Next question. Can integration of models and ecosystem health indicators be applied to our phenomena like sediment in the sea? Can this methodology be followed? Thanks.
I think like this, because Copernicus doesn't, in my knowledge, at least with the reanalysis, doesn't have anything sediment related. But this would be more Knut's deal, because he uses the open drift, which actually has sediment drift. I think that would be a bit more applicable here, because you really can't model. You can model how the sediment moves, but I don't think you really have good models to present what's in the sediment.
Okay, thank you. What is the temporal resolution of a model? Is it the time period between satellite overflights? Thank you.
If I remember correctly, the reanalysis was 2 kilometers by 2 kilometers, I think.
Yeah, I think something like
yeah.
that, yeah.
But the period between satellite overflights, that we haven't really concentrated on. We mostly did environmental assessment using just products.
Okay. Next question. Can you provide an example of an indicator or sub-basin where the current product performs particularly well and one where it performs poorly?
The central ones, which is the East Gotland Basin or the Bornholm Basin, those usually perform really well. But again, depending on the indicator, there are some nutrients are vary more, and essentially the Eastern Gulf of Finland and the Gulf of Riga are the ones with where the results are really, really, really variable.
Okay. Is it possible for freshwater small lakes?
These indicate, like, I'm trying to figure out the question, because these specific indicators are done in HELCOM, which are for the open sea areas or like big areas, because the lake indicators are, I think, different, and that again depends very much on the location and what you need.
Okay. Next question. Can this replace in situ field data collection?
That I would say no, because in the scientific community, there's this two sides that you can see, that one is only trust in situ, and the other one that is like, we have models. Why do we know anything else? And this is exactly what we try to do with the EROSI project, and now with this kind of work, is to bridge the gap. So essentially, the best version of it would be that you collect in situ data, which is then incorporated into the models, as with the reanalysis. this improves the model, and then model can be used to improve the timeliness and such in the environmental assessments.
Okay, thank you. And we have maybe time for last question very briefly. How do you measure inorganic and organic nitrogen in marine ecosystem? Satellite or MEMSA direct survey of data, or need to manipulate?
I think this is a more technical question for the models, because as it usually is done, it's with in situ. You go there, you actually take water samples. But yeah, I don't know if I am able to answer this question.
Okay, yeah, well, no problem. And we have more questions, but we don't have time for them. So of course, we're going to be included as well in a post-event report. So thank you very much, Oliver. And thank you all the participants for the questions. We are now moving to the last presentation of today. And it is a third user testimony by Alexandra Rosa. And well, I don't see the screen shared, but it's okay. I'll check. Yes, okay, it comes. Yep. So the topic is Madeira Coastal Insight, a Copernicus Marine collaboration. So Alexandra, we can see you.
Okay, thank you, Daria. I will share my screen.
Share the screen.
Okay, so good morning, everyone. My name is Alexandra Rosa. I'm a technical researcher at the Oceanic Observatory of Madeira, Arditi, in Portugal. And my talk will be about this project, which is the Madeira Coastal Insight Service. It's a project founded under the Copernicus Marine National Collaboration Program. But before getting into details about the project, I would like to start with a brief context about the coastal challenge that we face here in Madeira. So some of you may know that Madeira is an island, is considered a European Union autonomous region, has a complex hydrological network composed by several streams, which are characterized by having high altitude origin, which together with high drainage density and with the steep slope leads to high torrential flow and sediment erosion. This is particularly relevant during intense or extreme precipitation events, such the one that occurred on February of 2010, when extreme precipitation reached the island, leads to landslides in the high parts of the island, and then in the downstreams to flash floods, where it formed this coastal colored brown plume in the coastal area. A lot of human loss occurred and several damage in the main city. This is a very strong event in the memory of the Madeiran people. Of course, this had an impact which, together with the limited capacity of the wastewater treatment plants, which many of those has only preliminary or primary treatment level, can lead to water quality issues which can affect different kinds of economic activities that occur in the coastal area, such as aquaculture and, of course, tourism. So with this came the motivation to this project, where the main goal is to implement a comprehensive coastal monitoring service, where we integrate cutting-edge technologies and methodologies for real-time and accurate data collection, of course, aligned with European Union policies and directives. This project is not a scientific project. Of course, the science is all the time in the background, but this project pertains to provide service. And when we talk about service, we are talking about to ensure the sustainable management and protection of Madeira coastal waters, to guarantee compliance with European Union environmental policies, and of course to enhance local environmental management capacity. So in this project, we combine three components. As you can see in the right panel, we combine forecasts, remote sensing, and in-situ observations to provide this comprehensive monitoring service in order to provide information to support directives. So in terms of directives, we are considering 5 European directives, the one related with the Water Framework Directive, the one related with Marine Strategy Framework Directive, Nitrates from Agriculture Origin, Urban Wastewater Directive, and Bathing Water Directive, and also a regional legislative decree related with aquaculture that we have here in the coastal area. In terms of the product that we are combining, in terms of numerical modeling, we have been using a Copernicus data several years ago. In the left panel, you can see our coupled model that we have been running this operational model more than 10 years ago. It's able to, it's a coupled model, which is able to predict the conditions in the ocean, in the waves, and in the atmosphere, and the different kinds of the environments can change information information between them. You cannot see the movie, right? There, yeah. Okay, I will keep.
Doesn't seem like it's moving, no.
It's not moving. Okay. Anyway, I have a lot of movies, so that is not a good thing. But anyway, but basically, yeah, in the right panel you can see the configuration that we are using here in this project, which is from the ROMS model, where we use Copernicus model to feed our models, which has higher. Maybe I can keep playing. Okay, great. So where we can see that our models with higher spatial resolution are fed with CMEMS models, and then we have more downscale, and we are able to predict the condition around the island around 300 meters of spatial resolution. In terms of remote sensing, we have been using sea surface temperature and chlorophyll A products to monitor the conditions around the economic exclusive zone of Madeira. And in terms of in-situ observations, we implement a monitoring program on February of 2024 in the coastal area of Madeira, in the southern part, where is more density population. So we have wastewater treatment plants discharging here in this part. You can see also here some of the main streams that also outflows here in this coastal area. And we start measuring key water quality parameters with the ferry box, which is a wonderway system, very typically used in big research vessels. It's composed, this configuration is more compact for small boats, but is composed with different kind of sensors that allows us to measure temperature, salinity, oxygen, chlorophyll A, and so on. And we produce every month monthly reports available online in the Oceanic Observatory of Madeira website with the preliminary data sets. In terms of water column, we also deployed along the transit. We deployed fixed stations with the CTD, where we are able to see in real time the conditions of the water quality in terms of the same parameters than the ferry box, but also pH and turbidity. Okay, along the transit, we also collect water samples for further laboratory analysis, where we have an auto-analyzer that allows us to determine with very low detection limits the nutrient concentrations in the coastal area, and also dissolve oxygen and chlorophyll A. This is very important in order to validate not only the in-situ observations that we measure with the instruments, but also the conditions that we are predicting with the models. Besides that, we have also this vehicle, which is a USV vehicle. It's able to be remotely controlled, has different kind of technologies. We have Starlink for long-way communication, radar, of course, and it's equipped with echo sonder, which enables us to measure the bathymetry of the flow of the floor until 3,000 meters depth. But not only in the deep water, we can also measure the bottom, the bathymetry structures very nearby to the coast, around 5 or 10 meters depth, where we are able, with high resolution data, to identify, for example, the wastewater treatment plant's outfall pipes. Then we can use these information to configure our models. But of course, how can we actually provide services to the regional community with a lot of information and different kind of data sets? So the idea is to do it through two use cases. The first use case is focused on targeting sanitary risks in areas critical for tourism and aquaculture. So basically, this is a Lagrangian model, particle tracking model from the ROMS model with the high resolution configuration, where we are able to see the dispersion or the confinement of the plumes that come from the wastewater treatment plants. But in this project, what we want to do is not to have only this kind of pink color, but we want to have different kind of bacterial contaminations, including E. coli, in order to predict the vulnerability of passing waters and aquaculture farms to this kind of pressures. If you want to know a little bit more about these use cases, it's already available in the Copernicus Marine Use Cases portal, so you can see and learn a little bit more. In terms of use case 2, it focuses on assessing nutrient budgets, including sources, sinks, and cycling, using biogeochemical models, remote sensing, and in-situ observation. So currently, we already have the biogeochemical models running. As you can see, we can predict the nutrient availability and then the response of phytoplankton through the chlorophyll proxies. But the idea here is not only to have the predictions of the biogeochemical realm around the island, but also to implement the hydrological model in order to predict the discharges from the small rivers and understand the impacts on the coastal areas. Of course, the idea of both use cases is to provide real-time water quality reports detailing different kinds of information, including nutrient sources, sinks and cycling, and interactive maps. But of course, we want to provide service to the regional stakeholders and general users. We need to communicate with them. So in this sense, we did a session on the last April with different kinds of stakeholders, including local authorities, environmental managers, public, private companies, and of course the scientific community, with the objective of align expectations, what the people need, identify needs, and build a consensus on the features and priority of the project service. And the primary priority that was identified in these sessions was the need of a platform for data visualization. So currently, we are building this data visualization platform for Madeira Island, where we can see the aquaculture cages, the sea surface temperature from the forecasts. We can click, you can see in different kinds of points. You can see also the currents around the islands. And these colors, these particles are virtual particles that we are configuring that from the aquaculture cages that give us information about main circulation patterns that occur in this economic sector. Then we can click, you can see, sorry guys, this is still in Portuguese, but we can click and we can see specific conditions for that area. We can see here the sea surface temperature, predictions for every hour for the next 3 days. Then we can see the wastewater treatment plants locations and also particles that came from these sources of material. You can click in one particle, you see the exactly position, and then the end position at the end of at the forecasts. Then we can see also specific conditions for the bathing waters, including temperature also, and the tides. And of course, this gives us information about, okay, if one particle reach one specific bathing water, we can click and then identify the main sources of that pressure. The idea is not only to have here the forecast data, but also to integrate the in-situ observation, the remote sensing, and this platform have been co-designed with the stakeholders. So if you want to know a little bit more, you can reach me out by email or through the LinkedIn, me or Ricalde, which is together with me, the coordinator of the project, or you can check it out, the project website or the platform. Thank you.
Thank you, Alexandra. So it was a very nice presentation, and we have some questions for you. And
Okay.
yeah, of course, participants don't hesitate to ask more, because for now we have not that much. So the first one is, how far into the future can the numerical model predict data?
So we have predictions for the 3 next days. Our intention in the future is to also, not in this project, but in the incoming projects, is to also integrate artificial intelligence in the way that we can predict faster and give more days of predictions, such the ones that Copernicus has for 10 days of forecasts.
Okay, great. Thank you. Next question is, what are the tools and software you're using for numerical modeling for spatial analysis?
So yes, we use Python, and in terms of models, we are using COAST and the ROMS models, but we run the models with Python tools. But the platform is being built with the R Studio.
Okay, R Studio. And the next question, and for now it is the last, what are the main challenges for civil engineers in using real-time data and GISA mapping to analyze pollution impacts on coastal environments?
I guess the big challenge here is, how can we scientists or technical engineers or oceanographers work with data and integrate this data in order to be user-friendly and to reach the needs of the stakeholders. I guess that is the main challenge that we face. If we want to provide actually services for real needs, we need to communicate with the stakeholders, with the end users, and we need to work together with them.
Okay, thank you.
Thank you.
We have another question actually coming. Is the model output publicly available, and if yes, where?
Yes, through the platform. Then at the end, I will send you, Daria, the presentation, and then through the QR code or the link, you can access the platform. At this stage, we are not yet build the functionality to download data or figures, etc. But in the future, we will do that also through the platform.
Okay, great. Yeah, exactly. All the information will be also provided, all the resources on the official page of the event. So the next question is, why was RStudio preferred for building visualization instead of Python?
This is a good question. So this platform that we are building now is not the first version that we have. The first version was from RStudio, and in the scope of this project, we intended to pass this platform from the RStudio to the Python, but were some specific libraries that were not so feasible to us to work through the Python, and were more feasible working with through the RStudio. But I have not this information here, but If you want, I can share then specific libraries that we have some difficulty on working through the Python.
Okay, thank you. And next question, regarding code WST system, validating coastal regions, what observations are most crucial to ensure model reliability near the coast?
I would say currents. We really need currents. Here in Madeira, as you can see, the coastal morphology is not so regular, you know, it has a lot of irregular, not so regular. And also the bathymetry, we are in oceanic region. So in 20 minutes by boat, we reach already 1,000 meters. So the bathymetry has very steep slopes, and that changed a lot the currents dynamics in the coastal area. So I would say the currents here is the most critical for model reliability.
Okay, thank you. That was the last question we have. I don't know if we can wait, maybe, well, in any case, you can still put your questions on us through the QR code, and we can answer them later in the post-event report. And for now, we'll finish with this Q&A session, and I am giving floor back to Florian to give you some last remarks.
Thank you, Daria, and thank you to all our speakers today. I had just one last reminder about the replays and the polls. So you'll find both of these on the event website through the menu at the top of the page. We will also send you an email to let you know when the replay is available and a link to the poll about today's webinar. If you like to go further after today's session, I encourage you to visit the Copernicus Marine Service YouTube channel, where you'll find a rich library of webinars and training sessions from the past few years, all freely available. Each video focuses on a specific theme, whether a region of the world, a blue economy sector, or a practical example of how ocean data supports real-world application. So it's a great way to deepen your knowledge at your own pace and explore use cases that match your interest. You can also discover all Copernicus Marine events, both upcoming and past, via the Events tab in the top right menu of the website, where you can open any event page for details and registration. And thank you all for joining today's session. We hope you found the presentation insightful and that you discovered new ways to use Copernicus Marine Service data to address water pollution challenges. Before we wrap up, I'd like to invite you again to join us on Thursday, 18th December at 10 a.m. CET using the same link. This next session will be a hands-on workshop where we'll dive into practical tutorials in Python, QGIS, and R, all focused on water pollution and how to work with CMS data. So it's a great opportunity to put today's concept into practice, so don't miss it. We look forward to seeing you there, and I thank you again all for your participation today.